Good morning, girls, and welcome to your first virtual chemistry lesson. What a time to be alive. Um, Obviously, we are in quite uncertain times with regards to your chemistry education at the minute, so based on what we know at the minute, you're off Wednesday, Thursday, and Friday, and we'll be back in on Monday, assuming nothing changes. So, what me and Miss Doherty thought would be the best thing for you to do at the minute is spend this week going over the end of your redox potential topic, particularly fuel cells. Make sure you're happy with it, do the past paper questions, and then hopefully if we're back on the Monday, we'll go on to transition metals. So to help you with that, I'm recording this video where I'm going to talk you through the notes and specification in terms of what you need to know about these cells or batteries at the end of the topic. Now I can't promise it's going to be the most slick educational video, but hopefully it will be better than nothing. So how I propose going through it, I'm going to go through it just on pen and paper in front of you here, try and explain the best I can. Obviously you've got the notes as well at home, so read through them as well. If something doesn't make sense, I'd suggest you either stick a comment in the Google Classroom below this video or send me or Miss Doherty an email and we'll happily reply to it. Once you've gone through that, I think the best thing would be to look at the past paper questions. We gave those to you in school in the past week, and we've got questions on fuel cells. I've put the document on the Google Classroom as well, so you can download them if you've lost them. So hopefully between this video, your notes, and the past paper questions, you might be able to get your head around these commercial cells at the end of this topic. And it might keep you sane as well, doing a wee bit of work when you're stuck at home. So on to the topic itself. So the way this finishes off is in three sections. So we've got commercial cells, basically it just means batteries. We've got three types we need to know about. We've got primary cells, which are more commonly known as non-rechargeable cells. Secondary, the difference there being is they are rechargeable. And then you've got fuel cells, which are more kind of to do with power supply, so in terms of like powering the grid. And the one example we've got is a hydrogen fuel cell. There's one example of a primary one you might to know about, the zinc carbon cell. It's probably the one you have to know about in most detail. Then you've got three examples of secondary cells, the rechargeable ones, the nickel cadmium, the lead acid cell, and the lithium ion cell. So these look a little bit more complicated than the redox cells we were looking at the start of the booklet, just because the equations look a little bit more complex. What I want to try and get across is that they're actually not too far different from the standard redox cells we've looked at. So if we go back there, if you just see how slick that was, this is the one you're more familiar with from the start of the topic. So you've got two half cells. The convention dictates that the oxidation half cell has to be on the left and the reduction half cell has to be on the right. The oxidation half cell involves the loss of electrons. So in this case, zinc is losing electrons from this bit of zinc metal. And those electrons are moving from left to right, and that would give a positive EMF value, so electrons moving left to right. The voltmeter would be positive, so that's a positive EMF, we call that. The electrons would travel around to the copper half cell, where they'd be reduced, and the copper would gain electrons. Because the oxidation half cell involves the loss of electrons, it therefore must be negative, because if you're losing electrons, you must have a build-up of negative charge, so they're repelling each other. Similarly, if we're calling this reduction half cell, where electrons are being gained, they must be being gained on this side because this side is a little bit more positive. So the convention is that the oxidation electrodes on the left with a negative charge, the reduction electrodes on the right with a positive charge. Another key feature of this standard cell is the half equations that go alongside it. So again, with our oxidation 1, the electrons should be being lost. So as zinc is losing electrons, becomes zinc 2+. The copper 2+ gaining electrons to form copper again. So again, electrons being gained, and that's your half cell for reduction. As you know, a standard question would be to give the overall ionic equation for that for the redox cell, and that would just be a case of adding two half equations together. So make sure the electrons cancel out, two electrons, don't need to multiply anything up, add two sides together, the electrons should cancel out, and that is your overall half equation. So that's obviously a very simple version, one hopefully you're reasonably familiar with. It's worth keeping that in mind though, because when we look at the slightly more complicated ones to do with batteries and cells, they don't look as nice, but the key features are still the same. You will always have an oxidation and reduction electrode. There will always be a half equation with those oxidation reduction electrodes, and then you'll always be able to combine them together. So even if it does look a bit more complicated, this is still identical, the concept here. Two different half cells, two different equations, one overall equation. So if we look at the first one, so the first one to look at is the zinc carbon cell. This is your example of a primary cell in that it does not, it can't be recharged. So we'll start with the equation. So just keeping that same kind of pattern what we looked at with that standard one for the zinc and copper. You've got an oxidation and a reduction half equation. As I said, these look a little bit more complicated than the ones we're used to, but this is our oxidation half equation. So zinc is being oxidized. It's been oxidized to zinc 2 plus for the loss of 2 electrons. So hopefully not too scary there. Standard oxidation process going on here. Reduction looks a little bit more complicated. What you've got is manganese oxide is being reduced. That involves the gain of a water molecule, an electron, and that will go to this strange looking thing here, which we call manganese oxide hydroxide, plus a spare hydroxide ion over on this side. Okay, don't need to talk too much about that. That's a straightforward oxidation. This one maybe seems a little bit less obvious. The thing that's actually changing is the manganese here. So if we look on the left here, we've got straightforward manganese oxide. If we do a wee bit of analysis on oxidation states, oxygen has got a -2 charge. So there's 2 of them, that gets -4. Therefore the manganese must have a +4 charge, or we give it oxidation states, we call it a +4 oxidation state. This thing looks very strange here. Now it is just a manganese ion attracted to an oxide ion and a hydroxide ion side by side each other. That's why the hydroxide's in brackets to show it's one particular ion. We do know about these ions though. An oxide ion is 2-, and a hydroxide ion is only 1-. So 2-, 1-. From these two right hand side things, we've got a 3- charge. Therefore the manganese must be a 3+ charge. Therefore its oxidation state is +3. From that, hopefully you can see that the oxidation state of the manganese is changing from +4 to +3. That is reduction, and that confirms why we've got an electron here. The electron is being gained by that manganese to turn it into manganese oxide hydroxide. The water and the OH- are just the band side. The H is needed for, the oxygen and the H is needed for this hydroxide ion here. So it is essentially a wee bit of learning, but as long as you understand the fact that that you can keep track of the oxidation state of the manganese, that's showing it is reduction. In terms of making this into one equation, it's just what we did before. I do need to do a wee bit of multiplying up because I've not got the same number of electrons on each side. So we're going to double this one. And then a straightforward case of adding them together and cancelling out anything that is the same on both sides. So zinc is going to be there. 2 manganese oxides. 2 waters. Don't need those electrons because the electrons are the same on the other side. So it's going to zinc 2+, plus 2 manganese oxide hydroxides, plus 2 hydroxide ions. So even though this looks very long and complicated, that is essentially what the equation is in this battery. Now, a little bit of a difference with the zinc carbon one is that you are meant to know a little bit of detail what it looks like in practice in terms of what the battery looks like. The other ones you don't really need to know that level of detail. Again, it's one of the things that does look a little bit more complicated, but it's not as complicated as it looks. Essentially, imagine a rectangle. And everything's enclosed in that rectangle. So that's obviously a little bit different to our one we're used to, where it's in 2 different locations. These 2 half cells are now in one location within this rectangle, which makes it look a little bit more complicated. One important feature is this, though. This is what we would call a porous separator. And it's very similar to the salt bridge you have in your normal redox cell. Separates the positive and the negative electrode, or the oxidation reduction electrode. So what we've got on the outside is the oxidation electrode, the negatively charged one. What consists of is zinc. So the outer casing of the battery is actually the negative electrode, the zinc. Inside it you've got a zinc chloride paste. Now that's not particularly too important why you've got that there. Essentially connects the outside to the inside with something which conducts electricity because it's kind of semi-liquid, but it's not obviously a proper liquid. So it links up your 2 parts of your cell by being a little bit kind of wet. On your inside, you've got a couple of features. You've got this long rod going from the top to the bottom. That is a carbon rod. And outside the carbon rod, but inside the pore separator, is manganese oxide, which is what we recognise from this reduction half equation. So you actually have got your two parts of your redox cell there. You've got two different half cells separated by a dividing line as pore separator, which again completes the circuit like a salt bridge does, but doesn't allow the two things to mix across. These two parts here, if we go back here, these are what we represent by our oxidation half equation. The zinc is being oxidized. And these two bits here, whilst the carbon I have explained yet, it's not actually taking part in the reaction, it's just able to conduct the charge through the battery. So obviously this is made of graphite, that form of carbon, which is a good conductor but quite inert. So when the electrochemical reaction takes place, the current is able to go from the zinc on the bottom as you connect to your circuit all the way to the top and allow current to flow. So the carbon's just there for conducting purposes. The manganese oxide is the thing that's actually being reduced. So these two things together are part of the reduction half equation. Oxidation is negative by convention, reduction is positive, just like before. So make it sound a wee bit clearer to keep consistent. So everything around the outside with your zinc and zinc chloride paste is where oxidation is taking place. Everything on the inside, where you've got your manganese oxide, that's where the reduction is taking place. So you've got electron movement basically from the outside to the inside through that graphite rod and out the other side, and that will allow current to flow around your circuit. And again, those two parts are represented between these two half equations, which we looked at already. Okay, so that is our first and probably one of the most detailed commercial cell we have to look at. So let's move on to the secondary ones. Now, secondary ones, there's not actually too much conceptually different with them. The only thing you need to be aware of is the fact that they can be recharged in terms of if you flip them backwards into another circuit, you can make both reactions or both half equations go in reverse direction, but there's not too much extra theory with that. So the first one we'll look at is what we would call the nickel cadmium cell. And if we just jump straight in and look at the two half equations we got there, again, keeping that power in the same, we've got one oxidation half equation and we've got one reduction half equation. Okay, again, look a little bit more complicated, but we can just analyse them as they are. The oxidation half equation looks like this. Cadmium reacts with two hydroxide ions to form cadmium hydroxide. Now I've got to put some electrons in, but if I pause there, it doesn't actually look like that much has happened. You've got cadmium joining up to two hydroxide ions to make cadmium hydroxide. And on first glance that looks like it's it, but hold on, there is a change here. That's neutral cadmium metal, so therefore it must have an oxidation state of 0. There's no charge in it. However, if it finds itself in an ionic compound now, that must therefore have a charge because it's neutral overall. Two hydroxides gives two minus charges, therefore the cadmium must have a +2 charge now. The only way it can get +2 charge now, or an oxidation state of +2, is by losing two electrons. So the two electrons go on the right hand side, that represents an oxidation half equation. The reduction equation, again, looks a little bit more complicated, but it's actually very similar to one you have for the manganese oxide in the zinc carbon cell. What you start with is nickel, oxide, hydroxide. It gains a water, and it gains an electron, and it forms nickel hydroxide twice because it's 2 plus charge, plus 2 OHs. Again, looks a bit complicated, but if we analyse again, we've got a similar change to what we had up here for the manganese, where we have manganese oxide with the manganese oxide hydroxide. We're starting one step further along with the nickel. It's already oxide hydroxide, but they're now both going to hydroxides on the right hand side of this equation. So, to analyse that, let's just look at the oxidation state. So we've got oxide here, 2 minus. We've got hydroxide here, 1 minus. Okay, so 2 minus, 1 minus makes 3 minus, that makes this +3. But over here, two hydroxides, 2 minus altogether, 1 minus and 1 minus, means this must only be +2. +3 to +2 is a reduction, it's gaining an electron there. So same as before. Essentially, the easiest thing is to just root learn that off. Combine them together again, have to do the same steps, have to make sure my electrons cancel. So 2, 2, 2, 2, and make this up to 4. In fact, I think I've made a mistake there. No, there should have been, there should not have been 2 OH there in the first place, should have been 1, so we'll make it back to 2. So apologies for that. Combining them both together though, we've got cadmium plus 2 nickel oxide hydroxide plus 2 H2O. Now, I'm not actually going to add in the 2 H's because they're actually going to cancel out as well as the electrons. So cadmium plus 2 nickel oxide hydroxide plus 2 waters will just go to cadmium hydroxide plus 2 nickel hydroxide. And that is the complete equation complete. There's no technical details to know here. There's no diagram like we have for this first one, just known as oxidation and reduction half equations and how to combine them together. You could of course be given standard electropotential values for these two and be able to work out an EMF, but we'll not worry about that for now. Okay, so that's 2 down, 3 to go. Next one is another type of secondary commercial cell, which is known as your lead acid cell. This is what's actually in car batteries. So your lead acid cell. And as it kind of sounds like, it's got lead, it's got acid. The acid actually is sulfuric acid. The equations look a little bit strange again here, but as long as you're willing to learn them and get them in your head, interpreting it isn't that bad. Again, you've got an oxidation and reduction half equation. Oxidation involves lead being oxidized. So it reacts with the hydrogen sulfate ion, which will come from sulfuric acid. That will give you the salt lead sulfate, needing an H plus left over because we've lost the H from there, and then plus 2 electrons. We'll look at why we need that in a second, because your lead at the start is neutral, 0 oxidation state. In this compound, ionic compound, sulfate's got SO42 minus, therefore lead must be plus 2. It's lost 2 electrons, those 2 electrons go on that side. The reduction electrode does actually still involve lead, so lead oxide here. So I'll write it all out, then we'll try and interpret it. So again, kind of interpreting with the lead, it's starting off in this slightly different form. Lead oxide, so that's minus 2, minus 2, minus 4 from the oxides, therefore lead must be plus 4. Over here, lead sulfate again, SO42 minus, therefore this must be plus 2. It's clearly being reduced there, and you see that gain of 2 electrons. All the rest of this essentially is just balancing all your other elements. You need the sulfate to come from hydrogen sulfate from your sulfuric acid. You need your H pluses to balance out the H's you're losing, and the H's for the oxygen to go with to make water. So it becomes a little bit of a messy equation. Again, it is just balancing. That's why all the mess is there. So again, it's a wee bit learning. Showing how to combine them together though, if you actually spot the electrons already balances, it's a case of adding together. Now, a few things are going to cancel out here though, so let's keep track of them. First thing to add is the lead, plus lead oxide. If you actually look here, you've got HSO4 hydrogen sulfate and another hydrogen sulfate, so they're actually going to be together. So 2 of them. You have 3 H plus here, but only 1 on this side, so actually going to cancel that down by 1 to make 2 H plus. Giving the following products of 2 lead sulfates, because they're both on the right side, and 2 waters. So again, a little bit of work to do there, but if you just kind of are careful with it and make sure you're keeping track of what's coming together and what's being cancelled out, that will get you the correct half equation for that lead acid battery. Final type of secondary cell is the lithium ion. That's the one which is in your phone and most electrical appliances. This one looks deceptively simple, and there's a little trick, a little like quirk with it. Again, it's not too different because you still got an oxidation and a reduction half equation. Oxidation one is very simple. It's just lithium, includes in the name, lithium half cell for lithium ion battery. Oxides to form a lithium plus ion and an electron. What's a little bit different about this one is that lithium and that electron actually will travel through the circuit together, so it's not kind of held together by a salt bridge or a separator, and they will both travel to the reduction electrode, the positive one. What happens there is the lithium plus and the electron, specifically the electron, will attach itself to what it finds at the reduction electrode, which is cobalt oxide. That compound is there. What cobalt oxide will do is it will accept that electron and become cobalt oxide with a negative charge. So this is neutral overall at the minute. So the oxidation state of the cobalt is plus 4 from 2 oxides. it's going to form the cobalt oxide negative ion. And how it's done that is the cobalt has actually gained an electron. If this cobalt's now +3 and there's still -4 with the oxides, overall the charge will be minus charge. The reason the lithium is still here because it actually joins to make an ionic compound with that cobalt oxide negative ion, which gives you lithium plus cobalt oxide negative charge. Just take that out of the way, make it a bit more clearer. So that's your final compound there. It's a little bit different in that your products of your oxidation half equation actually move across through the battery to join up at the reduction half equation, but it's just an electron being gained by your cobalt to make your final compound. Again, combine them together, make sure the electrons cancel out, and they do because they're one on each side. So lithium will join with cobalt oxide. Now, if you actually think there's lithium plus on that side and this side, so they actually will cancel out as well as the electrons, and that will just form together your compound. So it actually looks very straightforward and trimmed down once you've got that those two things combined there. Okay, so that's your 3 secondary and 1 primary cell looked at. Again, there's no real difference how the content looks for them. It's just basically half equations and combining them together. Last one is slightly different to fuel cell, and I say slightly different, again, a lot of it will be the same. It's basically half equations. Fuel cell is a little bit different in that this has obviously been intended as a way of supplying power by using a fuel. The fuel actually used here will be hydrogen, and in the case that you look for in your specification, it's hydrogen under alkaline conditions. We'll start by looking at the half equations first and maybe try and understand why this is a wee bit different. Again, we'll keep that power in oxidation reduction half equations. Hydrogen is the thing you're going to oxidize, so we'll give you the half equation for it. Again, it looks deceptively kind of straightforward equation. The key thing to analyse is your hydrogen. That's an element hydrogen, it's got an oxidation state of 0. However, when it finds itself in water, it's going to be its normal compound form, which is +1. Therefore, the oxygen has been oxidised 0 to +1. There's 2 of them, that's why you got 2 electrons there. The OH minus is showing this is under alkaline conditions. Reduction, it's actually your oxygen, which is your other fuel source, combines with water and 4 electrons to make 4 hydroxide ions. Again, the thing to keep track of is the oxygen, starting off in the 0 oxidation state. In this case, it's in the compound, it's -2. That's a reduction, 0 to -2. There's 2 of them, so we've got 4 electrons altogether. So when we're talking about a fuel cell, these are the 2 fuels, hydrogen and oxygen coming together. We'll combine them quickly here, because again, that's no different to what we've done before. Going to need to do a wee bit of doubling, because I've got 4 electrons here, but 2 up here. So this needs doubled, so 2, going to change that to a 4, change that to a 4, and change this to a 4. Add them together, gets me 2H2 plus O2. Now, if I look carefully here, there's 4 OH on this side, 4 here, so they're actually going to cancel out as well. If I look here, there is 2 H2O and 4 H2 over here, so that's going to partially cancel out on this side, and the electron's going to cancel out. Actually only goes to 2 H2O on the right hand side, and that is actually balanced. If you think about that as an equation, that's one you are familiar with. That is just the combustion of hydrogen to make water, which is very exothermic. That's your squeaky pop test. All you're doing is harnessing it in a different way using electrochemistry. So they're in 2 different half cells now, but still reacting together.